such a material that after the life that the material is like a landfill or a pollutant, then we would not prefer to use that material. But if it is a material which is a recyclable material, for example aluminum, steel, it can be recycled to make another product, then it's a good choice. So we will use also during this life cycle that while the product is in the use, then we should avoid making such a toxic hazardous material which can cause environmental pollution plus toxins to human beings. So this is the life cycle design. Even from the concept to the manufacturing phase, all those steps we have to take care of the steps which we are trying to follow. The next life cycle, the next practice is design for manufacture and assembly. Please write it down. The next phase, design for manufacture and assembly. And what it means that any product, for example, if I consider a car, then a car needs to be designed and manufactured and assembled such a way that easy to manufacture. If the product is difficult to manufacture, it will have a high manufacturing cost. When it has a high manufacturing cost, then we will have to pay large amount of money, the cost increases. The economical aspect, we have to consider that into our heads. So assembly and disassembly is important. For example, if we make difficult for example car engines, they make difficult for the car engines to get assembled and disassembled, then sometimes we have to do some repair work. Then we have to disassemble some parts and reassemble back. So you see some cars, for example German cars, they are well known for their difficulty in the disassembly. That's why the repair cost for the BMW and Mercedes is higher as compared to the Japanese car. So we have to consider this when you are designing a product. The product should be designed that the manufacturing cost should be lowest possible, and assembly and disassembly is easy for the product. This is also the current practice. Design for quality. Please write down the third current practice, which is the design for quality. And what quality means, there are two definitions of quality. One is the removing the defects from the manufacturing phase, and plus the customer satisfaction. How would you satisfy the customer? So let me show you a chart which will explain you that if we implement that technique of quality improvement continuously, then we can decrease the defective parts from 70,000 parts per million to 124 parts per million. So in this graph, this is our in chapter 1, you see the quality has improved by implementing the continuous improvement method. From week 1 to week 7, the defective parts have been reduced from 69,000 to 124 parts per million. How did that happen? When the managers they applied the continuous improvement model, which we will learn later on, Taguchi method, TQM method. But they found the defect coming from the first week. Second week they found the defect was coming from the PCB, which was the printed circuit board, which is a vendor, contractor, another external contractor. They found the PCB has some flaws, defaults. So they hired another contractor, and the PCB supplier was changed. After changing the PCB supplier, the quality was improved from 70,000 parts to 42,000 parts per million. So you see the rate has decreased. The third change which they made, the reduction of misaligned contact pad defect due to the increased operator awareness. So by teaching the machinist that if you follow this method like checklist, then you can reduce the number of defects. So we have to keep in mind that the machinist should be also knowledgeable that what he is doing. And it is good practice that in a machine shop you put a chart, a poster that these are the checklists. If you follow this checklist, then there will be less chances of having a defective part. And then they found another improvement over here. It was not seated, the PCB not seated to the base. And when they removed that part, that defect, and the parts went down, the defective parts went down to 124 parts per minute. So that's an improvement method. Do you understand that? And the fourth current practice is faster design cycle. Please write it down. Faster design cycle. What I mean by that these days we have computers available. So you can make the drawing and simulate the drawing so that it is in a real user's hands. So the turnaround time from the order from the customer back to the customer is very short. So faster design cycle. So if I request the company to make this car for me, custom made car, so they will follow those guidelines and they will make a design in the computer. So computer aided design tools such as Pro-E, SolidWorks, CATIA, other tools are available, and ANSYS, this is also the FEA analysis. What will happen? They will see the simulation in the computer. So in the early ages we did not have this facility, so we had to do the math by our hands. Now we can do in computers. So that's how we can reduce the turnaround time and using these high-tech tools. And another practice is engineering without walls. Practice number 5, engineering without walls. What I mean by that nowadays we have internet, the facility of internet or networking. So if you are sitting in USA, you can coordinate with a vendor in Japan. So engineering without walls means you don't have to have a same building. You can contact the other people in a different country because of the facility of having the internet. The faster internet and networking will help us to make the product faster, to communicate at the same forum using tele-networking. So the last, okay, this is again the same thing. Salvage or recyclability. This is the meaning is the life cycle design, that if you can recycle the material, it's a good material. Or reuse, there is a difference between reuse and recycle. In reusing that, you will reuse the same product by repairing it. By replacing the old parts and putting the new parts, the life cycle will increase further, but there is a limit. So this diagram I'm explaining that if you increase the number of functionality, the cost will increase by adding more features into the product. For a chair, it has some armrests, footrests, backrests. So as you keep on increasing the number of functions, the cost will increase. That's what I'm explaining here. And in this diagram, I'm explaining to you that this is a tolerance. Suppose this is 1 inch. It's not 1 foot. So 1. Suppose this is 1 plus 0.1, 1/10 of an inch. Then the upper limit is 1.1 inch. The lower limit is 0.9 inch. So let me tell you. So if you give this loose tolerance as compared to 1/100th of an inch, okay, 1/100th of an inch is difficult to manufacture. The person will use the tools many times to have a finished cut to generate this much tolerance. So it is better to give a loose tolerance if you can perform the same functionality rather than giving a very tight tolerance and increasing the manufacturing cost, because tooling is required to have this much precision cut. So it's a good practice to reduce the to have a loose tolerance to reduce the cost of manufacturing. The design for quality, I already explained to you that this is there are two meanings. The customer should be satisfied, plus the defect should be removed. I already explained to you the faster design cycle. Because of the CAD tools and other technical tools available, the turnaround time is very short. So engineering without walls because of networking, and the design for export. What is the meaning of design for export? So if I'm a manufacturer, I will try to increase the marketing for 95% of the population. And for example, if I'm manufacturing a shirt, I'm manufacturing shirt for adult sizes from large, medium, small. Then what will happen? How would I know that what is the size of human being shoulder to shoulder, waist size? So there is a table in our book. So if you take a look, I think this, yes, this table. This table is telling us if you suppose I'm manufacturing shoes. So the upper limit for shoes, this is the shoe size for male men, and it is 12.6, so 97.5th percentile. And the lowest size is 10.3, which is 2.5th percentile. From 2.5th percentile to 97.5th percentile, 95% of the male population shoe size is covered. So if I'm going to manufacture the shoes, I will look at the anthropometry data. This is anthropometry data, which tells us what is anthropometry? The human size measurements. This is anthropometry. So it is very useful. So you can cover 95% of population. But below 92.5th percentile, you don't have to do that manufacturing. You can custom make for those people. And above 97.5th percentile, you don't have to make those shoes for those people. You can custom make those shoes. Have you understood this design for export? Okay, thank you. I will start the next topic. Thank you so much.
So this was a